It feels like forever, but really, we've only been able to observe gravitational waves for just like a decade or so, less. And yet, we've made these incredible discoveries about merging black holes, merging neutron stars. And there's a whole new set of gravitational wave observatories coming out that maybe will be able to detect merging supermassive black holes. There's the pulsar timing array that tells us about just the backgrounds of gravitational waves. It is a revolution in astronomy. And yet there are so many astrophysical processes that happen across the different wavelengths that there's like never enough telescopes to be able to observe this. Well, what if you could create a telescope and you didn't have to even invest any additional work into it? You could just take advantage of the kinds of things that are already out there. So my guest today is Dr. Lorenz. He's a postdoctoral research fellow at the Niels Bohr Institute, and he is proposing that for an upcoming Uranus mission, they could just listen to the radio broadcasts coming from that spacecraft and use that as a way to detect changes in the distance to the spacecraft as evidence for gravitational waves, detection of dark matter, and other astrophysical processes. This is a really fascinating interview. It's the kind of thing that I like, where it's a very easy sell because, in theory, if there's already going to be spacecraft going into the outer solar system, then why not take advantage and use this as a gravitational wave observatory to do more science? So we talk about this and sort of not only existing spacecraft, but also sort of how could you turn this idea into sort of like its perfect version of a space-based gravitational wave observatory. And then we shift gears and we talk about Lorenz's other work. So one of these is, how did those first supermassive black holes form? Did they merge by multiple small objects coming together, or did supermassive black holes just collapse directly out of giant concentrations of gas? And how could we detect that? And then we also talk about how when black holes merge, it's actually a very messy process. And yet in the mess is a lot of information that you can learn about the accretion disk that is surrounding the black hole itself. And again, how could we detect that? So if you're interested at all in gravitational waves, I think you're going to walk away from this interview with a ton of new information. All right, enjoy this interview with Dr. Lorenz Zwick. Lorenz, you're in one of the most historically interesting rooms I think anyone I've ever interviewed is. Where are you right now?
Yes, so I'm in the Auditorium A of the Niels Bohr Institute. This is the place where the greats of the 20s and 30s of the last century essentially invented quantum mechanics, which is the major branch of physics. Actually, Fraser, you can tell me if I can just turn the computer, show this place a little bit.
Yeah. Sure.
It's a little bit underwhelming. It's just a completely normal room, but it's this. And
Right.
there's pictures on the walls of those times, etc.
Right. But at some point, Niels Bohr gave a talk in this room as they argued about the nature of quantum mechanics.
Yeah.
That's
Yeah,
amazing.
exactly. About the Copenhagen interpretation, basically just let's accept that we don't quite understand what's going on and keep having
Right.
these amazing results.
Yeah. Well, fortunately, 100 years later, it's all been sorted out. Everything's been figured out.
Yeah,
Um,
absolutely everything. Yeah.
so, all right. So I've got a bunch of things that I want to talk to you, but you came across my radar initially with an interesting paper that you published about using a mission to the outer solar system as a way to also do some gravitational wave research. So let's start there. What are you proposing?
Yeah, so I'd like to mention that this was a very colorful paper. We've had people from very different backgrounds join in, and it's more of an accident that I ended up leading this. A couple of authors of the paper we have been working tangentially on this topic for almost 2 years now. But the idea is quite simple. It's to kind of hitchhike a ride onto a mission that is supposed to do planetary science, that has some instrumentation on it that will be very useful to measure the gravitational multiple structures of the planets outer planets, in particular Uranus. So Uranus is rotating very fast and it's kind of squashed and it's also tilted in an interesting way. There's more specific scientific goals that the mission has, but it has this instrumentation to really find the details of the gravitational potential of Uranus. And this exact instrument, if you just turn it on along the way to Uranus, so basically from when the mission, the satellite leaves Jupiter and then slowly flies across the solar system to eventually find its destination, we're arguing that if you leave that instrument on every day, you might be able to do all sorts of interesting science that is technically not part of the mission requirements.
But specifically, you're suggesting that it could be used for gravitational waves.
Yeah,
So
exactly.
explain how.
Exactly. Okay. So, very, very bare bones, this instrument that I'm talking about is essentially a radar. It's called Doppler ranging. It's a communication through radio waves between the Earth and the satellite, which is able to measure the distance between the Earth and the satellite. And you can see why this is useful for interplanetary spacecrafts, just to know where they are. You know, these are tiny objects flying in the solar system. With these radars, you send a blip of signals. It takes some time to reach Earth. You know how far it is because we know how far light travels. But if you keep sending blips and if you have something that is weirdly shaking around the distance between the Earth and the spacecraft, for example, a gravitational wave, then you should be able to kind of add up this extra little motion of the spacecraft over many, many years, add it all up, and then figure out if something else is in there, basically, not just the spacecraft motion, but something else that is slightly perturbing this Doppler signal that you're getting.
And so, I mean, there's going to be the expected motions of this spacecraft due to both the propulsion that it used, as well as the gravitational influence of going past Jupiter, and who knows, if Saturn is nearby and so on. So you'll account for all that, and then you're wondering, is there something extra that is changing
Exactly.
its trajectory at all?
Exactly. So the assumption that we're doing is that one can subtract the expected trajectory of the spacecraft and look at the residuals. So what is left over from what you calculated, basically, from the trajectory that you calculated. And we know that some leftovers will just be there because of noise, just because, we don't know everything that is going on in the solar system. Maybe there's some extra asteroids. Maybe the sun is pulsating in that particular moment. There's many, many, many sources of noise. But within that noise, if there's something that is coherent, that is oscillating back and forth, this is a little bit of a smoking gun for a gravitational wave, essentially.
And you suggest not just gravitational waves, but potentially, say, the interaction of dark matter in the region as well. So there's like other stuff that could be picked up by this trajectory.
Yes, what this mission would be if what we propose is will happen and actually works as we hope it will and calculated that it might. It's essentially like a gigantic ruler that is basically the size of the solar system, and anything that would push things apart and closer together in a way that is coherent, meaning that it oscillates back and forth, can be potentially detected. And actually, I can tell you a little bit of the progression. We were really interested in gravitational waves. That's also what I do my research. But it was interesting because um, we got some interest from two cosmologists that are on the paper. And they said, look, guys, this is exactly the type of signal that, for example, some models of dark matter would get you. And that was quite interesting. And we were happy to include this part in the paper.
Now, I mean, there have already been anomalies detected with the motions of spacecraft. Most famously, there's the Pioneer
Yeah.
anomaly, and it turned out to be heat coming off of a part of the spacecraft. There have been other interesting anomalous accelerations to spacecraft. Do you think there would be a way to be able to, I don't know, like are you anticipating that there will be anomalous accelerations already that will overshadow any kind of more subtle effects from gravitational waves or dark matter?
Yeah. Okay. So this is, I think this is really the crux of the point, because we did the best that we could as to model these noise sources, not knowing the official mission trajectory, which is still not decided, not knowing the shape and the engineering properties of the spacecraft, which are also not decided upon. So what we did is essentially we pretended that the spacecraft was similar to the Cassini mission. But of course, the Cassini mission was only turned on when it was orbiting Jupiter. And this mission, instead, we are proposing that this instrument, we're proposing that it should be turned on for essentially 10 years in a row as the spacecraft leaves Jupiter and travels towards Uranus. So we tried to model this the best we could, but unexpected things are, as the name implies, unexpected. And so this mission will fly in 15 years. We're hoping that people in the meantime will be able to figure out some more unexpected things. But at the end of the day, once you receive the data, you have to be extremely careful. And the Pioneer anomaly is one such example where people were claiming all sorts of things. For example, modified gravity, or even more exotic things, before it was understood that it was just an engineering problem, essentially.
Right, right. Now, there are already spacecraft out in the outer solar system. There's the Voyagers, there's New Horizons. Is there any way to be able to use these existing spacecraft? I mean, they have ways to communicate home with Earth. Is it too late? Are they already too far away?
Oh, actually, very interesting. We didn't think about the Voyager ones, but the Voyagers, they only blip occasionally to save battery. Also, the Voyagers are too far at this point, because in order to detect gravitational waves of a specific frequency, you need a detector of a given size. And it just happens that kind of solar system size is exactly what is required to detect gravitational waves in between what is currently almost been detected with pulsar timing, with stars, basically, how stars blip in the sky, and with proposed laser interferometry devices like LISA. This is a gravitational wave detector that will fly also in the 30s. So kind of we're in this sweet spot where we can catch gravitational waves, maybe that other experiments would not be able to catch. And Voyager is too far. But the real problem is just the fact that Voyager, the battery is almost dying. Also, it's technology from the 70s. So I'm just speculating here, but I would imagine that the noise levels are much higher than what we need. And but actually, it's interesting. We didn't think about Voyager.
Oh, good. Well,
Yeah,
there
yeah.
you go. But you did think about New Horizons.
We did think about New Horizons. New Horizons is a completely different beast, because it was just shot towards Pluto on a trajectory that the point was to get there as fast as possible. And also, all the instruments were shut off and then only turned on for the flyby, and then shut off again. And what we actually need is to track the spacecraft continuously for all of its cruise in between the planets. So we thought about it. We tried to get our hands into the New Horizon things, but at the end of the day, it was not what we needed, essentially.
Right. But even if it wouldn't necessarily work as a detector, maybe it could help you set some constraints on background noise
Yeah,
levels, things like that.
The problem is that this ranging data just doesn't exist for New Horizon, because I believe it was shut off most of the time in the
Mm,
cruise.
right.
So yeah.
So let's talk about the wavelengths then. As people are familiar, there's the ground-based observatories like LIGO, Virgo, Kagra, able to detect merging stellar mass black holes. There's the pulsar timing array that's helping us detect the background gravitational waves, probably of merging supermassive black holes. Upcoming LISA, other maybe Einstein telescope. There's a lot of interesting gravitational wave observatories that are in the works right now. What wavelength, what kinds of things do you think that you would be able to detect from this kind of a probe?
Yeah, this is very interesting, because this specific band, that the microhertz band, so around 10 to the minus 6 hertz, is exactly in between the things that we kind of know should be there. So from an astrophysical point of view, for just, we believe that these massive black holes are indeed there. We can see some indirectly. PTA has provided us with a lot of evidence that these massive black hole binaries are out there, and actually that there's a lot of them. But PTA can only see kind of the bulk, all of these signals from all the massive black hole binaries added up in a sort of white noise or red noise type of deal. We have actually seen that if everything works as we calculated that it should, so basically if there's no unexpected things that kill the sensitivity, that we should be able to see individual black hole binaries. So just see one gravitational wave signal from one binary. And this is a little bit different than what PTA can do.
What
PTA,
mass? Sorry, what mass of binary? Like supermassive black hole binaries?
supermassive black hole binaries, in between 10 to the 7 and 10 to the 8 solar masses, and at a frequency of more or less 10 to the minus 7 hertz, which still means that you're just seeing the two black holes orbiting around each other, but not becoming faster and faster, like the observations of LIGO, for example, where you really hear the acceleration of the orbit and the chirp. We would not be able to do that, most likely.
But I mean, there must be countless supermassive black holes in that configuration. How would you be able to pick out one from the ocean of these in orbit around one another?
Yes, you will only pick out the ones that are the loudest. So either basically the ones that are either most massive or
Mm,
closest, and closest to each other, because in that case the gravitational wave emission is stronger. And there's actually not that many that fulfill, given the sensitivity of a detector, there's not that many that fulfill all of these criteria.
right. I'm guessing, like with LIGO, I mean, one of the great things about, say, LIGO is you've got two separate detectors that
Mhm.
are detecting these things at the same time. So would it be better if they gave you budget for two and sent
Absolutely.
them in like perpendicular directions through the solar system?
Actually, let me jump in on a thing. If they gave us budget, I think this is something that we think is the selling point of our proposal, which is purely a theoretical proposal for now, is that it doesn't require virtually any additional budget, meaning that you don't have to put anything new on the spacecraft.
Right, of course.
The budget that we require is actually to track it, to have these big antennas operating for 10 years straight. But maybe we can talk about that later. This is a financial slash prioritization problem. But to the fact of having two satellites flying at the same time, that would be amazing, because then you have a gigantic, actually originally the proposal was to go to Neptune and Uranus at the same time, and that would have been absolutely gigantic triangle in the solar system. And then you could have, for example, localized these sources, because if you have two detectors at the same time, you can project the signal and then pinpoint where it comes from. And instead, with just one, you have this weird symmetry around the trajectory of the spacecraft, which means that the signal could basically come from any direction in a tube around it. And it will be really hard to say, well, it comes from this galaxy or this other galaxy.
Like this hemisphere or that hemisphere of the sky is it's like as much as you
Exactly.
get. Now as your spacecraft is, it's going to start at Earth and then it's going to make its way out to the outer solar system. Will the detection regime change over time? So will it start at, because I think what would be amazing is if it in any way overlaps, say LISA or any of the ground-based observatories, so that you could independently verify and confirm the detection of various events and then shift into a regime that you're then the only thing able to detect.
Yeah, that's very interesting. So the problem is that the actual trajectory of the spacecraft is not known, especially the part to get it to Jupiter, because you can do all sorts of cool gravity assists in the inner solar system to get it then to Jupiter. And then once it leaves Jupiter, then there's kind of only one way to go to Uranus, although there is still debate on how quickly it will get there. But what you're saying is extremely interesting, to have some kind of overlapping detection between LISA and this mission. The problem is that LISA will be most sensitive to slightly lighter black holes of around a factor 100. So it's possible that if we are very lucky, that we would catch kind of the lightest possible of the black holes that our proposal would be able to detect, at the same time that LISA detects one of the heaviest possible of its sensitivity. And there's like a little overlap in between these two sensitivity curves. If that happens, that is really amazing. But we actually didn't calculate the odds of this happening. It would be very interesting.
Yeah. I mean, it'd be great to independently, be like a distance ladder, right? You'd
Exactly.
be your
Yeah.
Cepheids to your Type 1a supernovae. But so it sounds to me like there's like the big advantage of this is that you don't need anything separate. You don't need to install any new instruments. You just say there's an instrument on board the spacecraft, turn it on, leave it on. As long as we have access to a radio dish on Earth, then we'll be able to continue communicating with it and everything is good and you'll get some amazing science. That sounds great. But it also sounds like you're going to give up a bunch of compromises. Gravitational assists sound like they're actually not very helpful. The speed of trying to get out to the outer solar system, you don't want to go fast. You'd actually be fine going a little more slowly to take your time. So let's imagine instead that there was, a decadal survey, someone, in the astronomical community said, we really want to understand the missing regime of gravitational waves and we want to design the right mission for the job and not have it piggyback on something else. Now you don't need a camera. Now you don't need any additional propellant. It doesn't need to be able to go into orbit or anything. You're really just sending chirping spacecraft in perpendicular directions, maybe three of them,
Oh yeah.
right at the same time. So what would be like the mission that would give you the most science without necessarily having to piggyback on an existing mission? And
Yes. So
I totally get, like, what I loved about it was like, hey, here's this mission. Let's add this extra thing. That sounds
yeah.
great. That's a way to sell it. Good job. Sold. But what would be the best version of this mission in your mind?
Yes. So okay, the best version will be at least two spacecraft in on 90 degrees. The more you have, the better. And the actually we've been thinking about this a little bit, and the real kind of magical sauce would be to upgrade the ranging from radio waves to a higher frequency wavelength, because higher frequency wavelength would kind of automatically, just by the physics of it, give you a larger precision, and more larger precision in the velocity that you can measure means automatically better sensitivity.
So like a laser.
essentially a laser.
Right,
So
right.
if you upgrade from radio to kind of microwave, you already get a lot. We were even thinking about optical ranging, which is something that has been kind of attempted with these mirrors that have been left on the moon, and they want to replace them. There's a proposal to replace those mirrors to have optical ranging between the moon and the earth. If we could have optical ranging at the level of 30 AU, 30 astronomical units, that would be a really a sensitive detector, and that would be amazing, basically.
Yeah, I mean, when you think about, I mean, NASA is already testing out laser transmissions as a way to send data home, with several missions as well as communications to the International Space Station. So it sounds like this problem of space-based laser communications is now getting
Yeah.
solved. Well, like the Psyche mission, for example, they're sending home almost, I forget what it is, like tens of megabits of communication speed with lasers to send cat videos home from
Oh yeah,
the Psyche
actually, yeah.
mission.
This cat
Right.
video,
Yeah.
we mentioned it in the paper. We actually wanted to
Okay.
leave a little joke in there, but at the end of the day, we decided, okay, we're scientists, no
Yeah,
sense of humor
there's
in
no room for
paper.
humor in science. No. Right. And so would you want to just like beam your transmissions back directly towards Earth, or would you actually want to bank them off of the moon, like use the reflector to try and get a couple of bounces off of it?
Ooh, okay, wait a sec. No reflectors. So
Right. Just go
the
straight to
thing that I
Earth.
mentioned with the moon was just directly between the Earth and the moon.
Right. Just using as a way to measure the distance to the moon. Okay, so you would send these spacecraft on 90-degree angles. They would have really nice lasers that are directed back at Earth, and then you
Yeah,
don't even need to use up radio time. You just have a telescope that can spot the
yeah,
transmissions
yeah.
in the way that NASA is already doing it. And it's a good test of this technology as a way for doing science. So maybe that's the other way you sell it. So
Yeah,
right?
yeah. It's already quite hard to sell it like this, just piggybacking. So we're going step by step.
Yeah, on a mission that doesn't exist yet, right? Like on a
That's true.
mission that nobody has planned out is the problem. But at the same time, this kind of laser technology is going to be necessary to make the LISA mission work. So it sounds like and they already did they did a precursor mission for LISA. So I think
Oh
there's
yeah.
another way to go about this. Well, that all sounds great. So then let's say we have made this sort of perfect mission, laser chirping spacecraft on a nice trajectory leaving. What does that get you from a scientific standpoint?
Yes. Okay, so there's all sorts of things that might be in this gravitational wave frequency range. I'm gonna start because I'm an astrophysicist. I'm gonna start by saying the ones that are essentially, if they're not there, is it's really weird. And these are these massive black hole binaries in the masses between 10 to the 7 and 10 to the 8 solar masses. Those are, essentially 1/10 of all galaxies should have a supermassive black hole in them. Galaxies merge, so presumably black holes merge. If you measure all of those, you can catalog beautifully all of these black holes that are big black holes that are in our universe. And there's all sorts of interesting questions between the related growth of galaxies and black holes, and the physics of how black holes sink into galaxies, and how black holes pair, because galaxies are very large and black holes are tiny with respect to the galaxy. So how the hell do they get to the center? Also, you can answer question how far away in terms of redshift black holes exist and merge. And this is also one of a big question in astrophysics. Basically, how large, how long ago black holes can be. Then, and this is here. This is not my research topic, but I've learned a lot by leading this paper. There's all sorts of interesting signals in this range of frequency that come from the early universe. There's the possibility by tweaking different fields and different couplings between fields in the early universe to produce gravitational waves. And this happened just by the dynamics of the fields. Fields are stress energy in terms of general relativity. So when they move in violent waves, in ways, they produce gravitational waves. And presumably these fields were behaving in extreme ways very early in the universe, where the temperature is super high and all things are kind of extreme. And there's specific ways in which the cooling off of these fields produces phase transitions in these fields, where the fields goes from an energy state to another one very rapidly. And these are almost, I don't know exactly how to visualize them personally, but I've heard people describing them as kind of bubbles that expand of these phases. And these dynamics of these bubbles, they can produce gravitational waves like any other thing that moves fast and is heavy.
Right. So the detection of gravitational waves, these primordial gravitational waves that would give you a way to peer into the universe before the cosmic microwave background radiation, and
Exactly.
maybe potentially confirm different theories of inflation or whatever is the early universe, however it
Exactly.
all
Well,
came
perfectly
together.
said. Yeah,
Yeah.
exactly. And
Yeah.
I think
Okay.
actually, let me add something. This is very interesting because, there's this incredible moment in the universe where it becomes transparent and you can see things. But this is for light. But gravitational waves, they can go through matter much more easily than light. And so if you see gravitational waves from the early universe, there's this idea of the CMB of being like a baby picture of the universe. Well, gravitational waves would give you not even a baby picture, they would give you like an embryo picture of the universe. So it's quite exciting, actually. I've been learning a lot about this also.
Yeah. Um, but then I can sort of imagine other kind of phenomena, like, say, black holes that are farther away from each other, other kinds of events. But is it just like you're going to be getting a very certain kind of wavelength? So it's really just supermassive black holes and primordial black gravitational waves, but not a lot of other phenomena.
Oh, I see what you mean. For example, just to normal stellar mass black holes, if you put them far apart enough, then they would radiate at that frequency.
Right, right,
But the problem is that the power, the amplitude of the gravitational wave would be tiny, completely minuscule. And in terms of gravitational wave detectors, the sensitivity that we hope to achieve, even in the best case scenario, is still much, much higher than, for example, LIGO. LIGO can detect gravitational waves of order 10 to the minus 22. And in the best case, if our calculations are correct and there's no unexpected noise sources, we would get 10 to the minus 15. So you need big things to produce these big
right.
gravitational waves.
I understand. Okay, all right. Well, that's all really exciting. And I think there's a lot of other missions that are in the works as well. I mean, there's the Interstellar Probe,
Tell me more. I
which
don't know about this one.
this is a plan potentially by NASA to send a spacecraft out to the interstellar mission, anyway, to like sort of super voyagers, like out into the interstellar space
Oh,
to try
wow.
and map the presence of the magnetic fields and particle counts and things like that. And that seems fairly well along, and sounds like it's sort of the same kind of thing. We could use a piggyback.
Oh,
It's
wow.
going to
Okay.
have to
Yeah.
communicate back home. And then there's ideas for like potentially the solar gravitational lens. You send a spacecraft out to 500 plus astronomical
Yes.
units away, but have to get out there the entire time, and you could be sending transmission. So it sounds like there's a lot of interest from various space agencies in getting spacecraft out to the
Out.
very depths of the outer solar system, and it's just a matter of asking if you can chat with the with the transmission system throughout the
Yeah.
entire mission. Yeah, that sounds really
Actually, I
interesting.
can be completely honest here, and maybe the fact that we focus on this mission is more of a legacy thing. It's just because one of the original people, Dennett, second author on this paper, he's a planetary scientist.
Right. Yeah.
And I think this idea came up. Actually, I can't remember exactly, but the Professor Prasenjit Sa, and then it's just brainstorming, and then I came in very early, and I think they were at a planetary science conference where this was mentioned. So maybe we're just running on some legacy
Yeah.
code, and it's worth just imagining
And
other.
anyone, yeah, you just stick your thumb out. Anybody who's going to the
Yeah,
outer
yeah,
solar system, yeah,
yeah,
catch a ride. Yeah, that sounds good. All right, so I want to shift gears because you work on a couple of other topics that are actually really interesting and are pretty relevant recently. So another field that you work in is this idea of sort of black hole formation, and one of the big outstanding questions in cosmology and astronomy is like, where did these giant supermassive black holes come from? How did they get so big
yeah.
so quickly? Explain how maybe direct collapse could be the answer for this.
Yes. So if you probably your viewers are very familiar with these wonderful JWST results that galaxies seem to be modern all the way back at redshift 10. They look like completely developed galaxies, and also JWSTs and other missions are finding these even more gigantic black holes even further back in the universe. This is a problem because at some point you just run out of time. So how do you make a black hole? How do you grow a black hole to a gigantic size? We're talking billions of suns, billions of solar masses in what cosmically just a basically an
Yeah.
afternoon. And traditionally there has been this idea that the first black holes were made from the first generation of stars, which actually, if I'm not confusing myself, is called the third type,
Yeah.
population
Population
three
three. Yeah.
stars. Yeah, exactly.
Population 3 stars. Yeah.
And these would basically run their lives and then form a relatively massive black hole. And then this black hole would basically just be force fed for 400 million years at the maximum possible black hole feeding rate perfectly, and then make these gigantic black holes. But people have started noticing that actually it's very hard to force feed black holes because gas has to come from somewhere. Normally, it comes from these streams that enter the galaxy, and it's you need various mechanisms to shock the gas and remove the angular momentum that keeps it orbiting around the galaxy. So I think in the 90s, 2000s, people have said, hey, what if we just start off with slightly larger black holes? So we pile up a bunch of gas in the center of the galaxy, and then instead of this black hole starting at 10 or 100 solar masses, for various reasons, it can collapse to 10 to the 4 solar masses. Then you kind of skip ahead the the hard the part of the lifetime where it's really hard to feed black holes, and you kind of skip a good bunch of the evolution. And this idea is called direct collapse. Why? Because you basically don't have to go through a normal star phase. You don't go through this typical evolution where you have a star and it runs out of fuel, so it explodes, but part of it collapses and it becomes a black hole. You just have a bunch of gas, it does magical things, and it all collapses into a black hole. And there's various models, various flavors of direct collapse. And something that I worked, and this was in collaboration with my PhD supervisor, is to just say, okay, what's the most extreme possible direct collapse scenario? And we were able to come up with a scenario that is actually quite well justified in terms of normal galactic dynamics, perhaps less justified in terms of gas physics, but maybe we can go into details later, where you have a situation where you really collapse already a supermassive black hole directly. So 10 to the 7, 10 to the 8 solar masses, you collapse it from just a ball of gas, from a disk of gas, actually. And it was a very interesting, and actually the new findings of JWST. I'm still in collaboration with my PhD supervisor. We're trying to figure out if they have something to say about this quite extreme model that we came up with.
I mean, I know that we're seeing supermassive black holes with like 1 billion times the mass of the sun that are 700 million years after the Big Bang.
Yeah,
I mean, that's a beefy black hole that
yeah,
it's already formed. So I know that when you look at individual stars here, say in the Milky Way, the largest regions of star formation, there are limits to the size of the most massive stars. It's somewhere in the 50 to 100 times solar mass
Mhm.
range, and beyond that point, as the star is starting to form, gas and dust heats up and it has stellar outflows that are so powerful, the stellar winds kick in, that no further material
yeah.
can accrete onto the star. And so it limits at the top end how big a star can get. So why would those limits not be there in the early universe?
Yeah, very good question actually. So these population 3 stars, they're special because they are the first generation of stars. So they have essentially no heavy metals in them or
Right.
heavy elements in
Right.
them.
Like oxygen or, no
Yeah,
polluted
metals.
metal.
Anything
Yeah.
above helium is a metal,
Yeah.
and for this reason, their evolution is slightly different than normal stars. And these outflows, etc., they can become larger because they have no metals in them. But this is still not enough to make direct collapse black holes. To have direct collapse black holes, at least you need to be in a situation where you build up a supermassive star. And a supermassive star can only be built up if you essentially, if the evolution of the star is strongly determined by the material that is falling on it, such that it never even has the opportunity to follow a normal star evolution. Here I'm simplifying a lot. I'm also not a stellar physicist, but I've worked tangentially with stellar physicists. Essentially, if you pile up enough material, if you throw enough gas on a star, its evolution starts deviating from the evolution of a normal star of that mass. And so you can essentially get more extreme collapses of black holes.
And so would this force feeding of the star, would that just be coming from the density of matter in the early universe, or would that be coming
Exactly.
from some kind of astrophysical process that is maybe magnetic fields or things that are channeling material in ways that the star can't get rid of it in time?
Yes. So this is actually the major crux of this direct collapse problem, is how to put enough gas all together in the same place. And there are one important thing that you have to avoid is that just gas spontaneously clumps up and forms smaller stars. Because you have
Hmm.
to imagine that these stars, you need them to reach thousands, tens of thousands, hundreds of thousands of solar masses. But there are also stars that have one solar mass. So how do you prevent the gas from splitting up and forming just a bunch of little stars? And there's many mechanisms for it. And the traditional one is to invoke the fact that there will be radiation from other population 3 stars that kind of heat up and keep this gas nice and puffy so that it cannot clump up, like basically like a gigantic UV lamp that you shine onto this ball of gas so that it stays heated up and does not fragment into
Right, because you
smaller
need cold
pieces.
gas to get star formation, and it won't work if you have
Exactly.
hot gas.
Exactly.
Oh, I never heard it explained like that. That's wonderful. Thank you.
Yes,
Um,
I think this is correct, but it's an intuitive explanation. There's more detailed physical reasons why this works. But actually, if I can plug in my own things, um, this proposal that we had is quite interesting because you can skip over you can skip over this step. You don't need these weird UV lamps. You can just have two galaxies smash in together, and then automatically the gas piles up in the center like crazy. just because you're taking two galaxies, all the gas that they have in them, and you smash two galaxies together and you get a bunch of gas inside.
Right. The density of matter in the area is beyond it attempting to break up into little stars that are
Exactly.
in
Yeah.
a globular cluster or something like that. Right. That's really interesting. So I guess what would it take to confirm that this is true?
Ooh, yeah. So so what that is true? Direct collapse or this specific
I
extreme
mean,
version?
well, both.
Oh yeah.
Direct collapse and I mean, it does. It definitely feels like supermassive black holes building up from separate building blocks is harder and harder to justify. That direct collapse, because Webb is seeing these black holes earlier and earlier in the universe at enormous masses, that direct collapse is starting to build more evidence. But what would it take to actually, what's the smoking gun that says, okay, yeah, direct collapse, and then this is the mechanism of direct collapse?
Yes. So actually, it's like two camps, right? Some people say direct collapse is gaining more traction. Some other people say super Eddington accretion is gaining more traction, which is this idea that you can force feed black holes faster than what you're supposed to do. But let's keep that completely on the side. I think the smoking gun, this is a very interesting topic. It's very hard to find a smoking gun because these things are supposed to happen by construction so far away. And also, they're supposed to happen by construction in a very gas rich region. And gas, its favorite thing to do is to block light. Uh, so actually, and this is something that my supervisor and I, we are quite keen on trying to convince that this is possible. You turn to gravitational waves because gravitational waves pass through everything, like we were mentioning before. If you the collapse of these very large balls of gas, as long as it's not perfectly symmetrical, it will produce a gravitational wave similar to the gravitational waves that you expect from supernova collapse.
Hmm. Now
Similar,
they would
but
be redshifted though into whatever 13.5 billion years ago.
yes, and it's also a much bigger structure, so automatically its frequency would be lower, and also it's redshifted, so again its frequency will be lower. And if you do a little calculation and you calculate basically a 10 to the 7 solar mass ball of gas that is collapsing at redshift 10, it exactly peaks in the LISA sensitivity.
Interesting.
Yeah, it's you get a frequency of at the peak of the burst of the gravitational wave signal at 10 to the minus 2 hertz. And the problem is that you have to be lucky to get it because LISA will be operational for around 4 years. And we did a calculation that for these very large balls of gas, how many are there, how many they're supposed to be, such that you don't get too many very big black holes because we can count them, right? And we calculated that you should get approximately 1 per 100 year. So there's like a 5% chance, approximately. Actually, is that right? Yeah, a bit less than 5% that you switch Lisa on and you find one. And even if Lisa sees a burst like this, then you have to think, okay, was it actually a signal or was it some glitch of some sort? But that's another whole set of
Right,
questions.
right, right. So then I guess like how long will that process take? So what you're saying is that if you count up the number of galaxies in the universe or the number of supermassive black holes in the universe, let's say there's, I don't know, a trillion, um, and then you subtract the amount of time that it would take that these things were happening, because these events are still so short-lived and kind of catastrophic, there's going to be a delay on how often they're happening, that Lisa may only see one.
Yeah, exactly. Because galaxies are long lived, so you can just look and you see them. But the problem is that these events. So actually, you can do the right. I said before that the frequency should be 10 to the minus 2. So the duration of this maximum burst is around 1 over 10 to the minus 2, which is 100 seconds.
100 seconds.
Yeah.
So you'll go from a very compact cloud of gas to a supermassive black hole
Yes.
in 100 seconds.
Well, the whole collapse might take more,
Yes.
but the peak of the gravitational wave signal will be at the very end, just a moment before it becomes a black hole. And the time it takes for light to cross a black hole of around 10 to the 7 solar masses is around 100 seconds. So that time scale kind of tells you more or less what's the most violent part
Wow.
of the signal. Yeah, it's insane. Yeah,
The universe is crazy.
astrophysics is amazing.
Yeah, totally. All right, so the last thing I want to talk to you about is your other work, and this is sort of thinking about how you could use gravitational waves to observe black hole accretion disks.
Yeah, all right. So this is actually my main topic of research. I think gravitational waves now, it's almost like a given, but they are a very young field of research, and it's only been 5 years since we detected. And I think it's very exciting to think, in the 60s when they figured out radio telescopes, look at all the things that came out of it. We're now basically in 65, right? The equivalent of 65 for gravitational wave detectors. And so I hope,
Like 1965. Like we're in
yes,
1965. Yeah, I understand.
1965, yeah.
Yeah, okay.
The idea is this. The leading question is this. Imagine you have a detection of a gravitational wave with LISA, and you measure the gravitational wave and you see that there's a little deviation from general relativity. And then you need to ask why is there. And there's a camp of people that says, well, maybe those deviations will be produced by modifications to general relativity. And those are the more fundamental physics type of people. And then there's the astrophysicists that say, well, guys, let's look in the sky. It's a mess. There's gas flying around. There's accretion disks. It's never the case that a binary of black holes is perfectly isolated. Odds are that there's a third black hole in the vicinity. Most stars explode and the gas stays around. So it's going to be an astrophysical mess. But this is exciting because perhaps the surroundings of the binary can influence the gravitational wave emission in specific ways. And if you measure and constrain these modifications to vacuum, to the perfect GR evolution, general relativity evolution, maybe you can reconstruct what is going on around the source of gravitational waves. And accretion disks are particularly interesting because we believe that many black holes will be dragged into accretion disks and then fed into the central supermassive black hole. So the accretion disk is basically the mechanism from which you get gravitational wave sources. And it's not like it just magically disappears once the source is there, once the binary of black holes is there and starts to emit gravitational waves. And me and also half a dozen or a dozen other people are really trying to think, what influence does the accretion disk have that you can detect through the gravitational wave? Does it leave some specific signatures? And if so, is it reasonable to expect that one can extract it from the gravitational wave? And if so, what can you say about the accretion disk that you would have not been able to say in any other way possible?
And so like when you have this supermassive black hole and it is feeding on smaller black holes, it's that accretion disk acts like the brakes, the friction that the black hole has to fight through, and what causes it to lower its altitude and eventually be consumed by the black hole. But it's going to be bringing blobs of that accretion disk with it, and that will tell you something about the physics of the system.
Exactly.
What feels like noise is actually really interesting in determining the size, the consistency, the density, and so on of the
Exactly.
accretion disk itself.
Exactly. Most in the simplest possible case, when you put a little black hole in an accretion disk, what happens is that you get some kind of spiral of overdensity, because the little black holes kind of pushes around gas close to it, and then the shearing of the accretion disk kind of distributes this gas, and you get these beautiful spirals. It's called the Lindblad resonance. And one spiral pulls back on the little black hole, and the other spiral pulls forward. And there's a little asymmetry that just gives you a constant push. Actually, sorry, a constant pull to the little
Mm.
black hole. And this constant pull is almost exactly as you said, as a brake. It makes it slowly lose energy and spiral into the big black hole a little bit faster than you would expect.
So,
And
so one of the sort of unsolved questions in physics is this final parsec problem, where
oh,
how do you get supermassive black holes to merge, because at a certain point they're going to get close enough together and then they will clear out their accretion disks and there will be no more forces that are bringing them together. So do you think this gives us a path to try and answer this problem?
no, unfortunately not,
Right.
because one parsec is very large, and the size of these gravitational wave sources for LISA, once they become visible in LISA, is 1 millionth of one parsec.
Right.
So
They
you have
are
to cross
really
over the last
close.
parsec problem even before making any gravitational wave source that LISA will see. So that is
So
a problem of how do you make the sources that LISA will see, and this problem of, yeah, that's like a one step up before.
right, right,
Yeah.
right. But in theory, Lisa should be capable of detecting the noise as it is, as a supermassive black hole is gobbling up material, and you think these are the kinds of detections that Lisa will be able to do.
Um, it depends on how thick the gas is around the black hole. So if there's not
Mm,
enough gas, it will look, up to the sensitivity of the detector, it will look like a vacuum source, a source with no gas at all. You need a certain threshold of density of material that is doing complicated things in order to distinguish it from no material at all. And then the more material you have, the more precisely you
right.
can determine these differences from no material at all.
But quasars, for example, are actively feeding supermassive black holes. They're surrounded by giant accretion disks, and so if you are able to make these detections with Lisa, then maybe you can match up individual quasars because they're going to be so bright and so active.
Ooh, so you're saying so let I think that you're saying that if there's like a very bright quasar, you already know that there's gas around it.
Right. Yeah.
And if Lisa also sees a gravitational wave vaguely from that direction, and it has some traces of other stuff going on, you can say, well, maybe it's the gas from the quasar.
Yeah.
Is
Yeah.
is this what?
That's what
Well,
I'm.
this is.
That's what I'm
Yeah,
saying.
I'm literally working on this right now.
Great. All
So
right.
congratulations.
Great. All right. Well, then there you go. You can put me
I'll
on the
put you
paper
in the
then.
acknowledgements, or if you want to collaborate.
All
I'm
right.
literally working on this
Yeah.
kind of thing right now. Yeah.
Oh, that's great. Great. Well, I'm telling you, unfortunately, it's beyond my pay grade. But, um, uh, so what are you obsessed with right now?
Yeah. So okay. So as you may have noticed, I do several things at the same time. Right now, I'm obsessed with the idea that people shouldn't orbit average. So what am I talking about? If you imagine two black holes and they're orbiting around each other, and there's all this gas doing complicated gas things around it. What researchers, what the field has done until now is to say, ooh, probably all this gas dynamics is complicated, but on average, what you will get is just the two black holes slowing down a little bit orbit by orbit. So maybe they go a little bit faster in or a little bit faster out. But if you look at simulations of accretion disks, it's just a churning mess. It's gas is flying out, in and out. There's these streams of gas that are intersecting in and out. And if you look at the forces experienced by the black holes, they are oscillating like crazy. You can really see that this is a complicated hydrodynamics problem. And if you just take the average, you lose all of these oscillations. You lose all of this complexity of the gas. And of course, it's easier to work with a constant force rather than a super messy, complicated force. But also there are techniques, if the force is so messy that the details really don't matter. There's also techniques for that extreme. And I think people have really underestimated, and it's also what I'm working on right now. If you go to the extreme where the forces are so messy that it's not really important to figure out the details, you just know that they are oscillating like crazy. That will also give some interesting insight on what is happening in accretion disks and how black holes interact with the gas around them.
It's got to be really interesting, when you think about how anything moving generates gravitational waves. And then when you think what in the universe is moving, well, kind of anything and everything. And so everything out there is generating gravitational waves. The question just comes down to our ability to
Yeah.
detect them. Like if there was an alien civilization that was driving cars around on the surface of their planet,
Yes.
that's releasing gravitational
Yeah.
waves, and you could theoretically detect that. But it's just that we don't have the capability to measure with that level of
Precision.
specificity,
And
right?
actually, not only you should be able to detect that, they're reaching us for sure. And this is really the
Yeah.
key cool thing about gravitational waves. It's just that they go through everything. So literally anything in the universe that is producing them, it will arrive here,
You
and
can't
we'll
hide.
have the
Yeah.
chance to detect
Yeah.
it.
Yeah. And so then you think about what we're capable of seeing. And right now it's just things with many times the mass of the sun crashing together at close to the speed of light.
Yeah.
But later on, maybe the regime of the kinds of astrophysical processes that we can detect will come down. And so it's all about the capability of the gravitational wave observatory.
Yeah.
Is there do you sort of imagine in your mind the perfect gravitational wave observatory that would give us the most capability? If money was no object, what would be the perfect gravitational wave observatory, do you think?
Okay. Yes, I can. And it's actually something that has been discussed as a out there proposal recently. I would do this ranging thing that I talked about earlier with lasers with every asteroid in the solar system. So between
Now we're
asteroids.
talking. Okay.
Yeah.
So you're
And
you're
I
you're
can't
range
remember the
finding off of
authors of
all
these
the asteroids?
proposals. Sorry, go.
You're range finding off of every asteroid in the solar
Yeah.
system? Okay.
Yes. I can't remember I wish I remembered the authors, but there's a paper on the archive about this recently, and it's just an idea that when you have a couple of beers with friends, you just say, you know what? Why don't we use all the asteroids instead of satellites, and just having a giant network of
Wow.
ranging lasers around the solar system
And so that would get you
from
every
asteroids.
wavelength. There'd be the near Earth asteroids, and there'd be the Kuiper Belt objects, and there'd be
Oh
stuff in
yeah.
the Oort cloud, and you would just be
Yes.
collecting every single wavelength at the same time.
Yes.
And all it requires is just a tiny little retroreflector
Yeah.
sitting on each asteroid. And
Yeah,
then
it's nothing. Come on.
yeah, it should be easy. That
Yeah,
sounds
but
great.
actually, if I may just, I don't know if we're finishing off, but how PTA works, pulsar timing as arrays, the fact that one is literally using stars and how they rotate and the fact that they shoot jets from their poles and that they are the most precise clocks in the universe. This is not what I work on, but I think in some kind of more poetic sense, it's beautiful that one can use stars to see gravitational waves passing through, and they're just like the perfect clock, and they're out there in the galaxy, beautiful. Yeah,
Yeah, so somebody already put
perfect clocks.
perfect clocks out there across the
Yeah,
entire universe. We
yeah.
just have to find them and read them. Well, Lorenz, it's a pleasure to talk to you. Thank you so much for taking the time to chat. Good luck with your research, and let me know when someone agrees to give you some observing time to watch the Uranus probe flying out into the outer solar system.
Thank you so much, Fraser. Really, really fun talking to you.
All right, take care. I hope you enjoyed this interview with Dr. Lorenz Zwick. Now, I'm going to give you some more thoughts about this, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Groth, David Gilton, and David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modzo, Paul Rohrbach, Stephen Krasaki, Stephen Fallon-Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. Well, this was a great interview. This was a real eye-opener for me and gave me a lot of additional information. I think you heard a couple of points where I kind of gasped and realized the implications of this. And it is just amazing to me how this entire field of astronomy, of gravitational wave astronomy, a completely different way to view the universe, is still just in its infancy. I mean, we have LIGO, we have Virgo, we have Kaga, we have other works in development, and yet our imaginations have only just scarcely begun in what this field is going to do for us and the kinds of discoveries and observations that can be made. And yet they are being made. And every day we are reporting on new discoveries and new insights. And to have this matched with potentially neutrino observations, with electromagnetic wave observations, telescopes, we're going to have this much better multiple view of the universe around us and really get some answers on some fundamental questions that humans have been asking forever. You know, how was the universe? How did it form? Where did it come from? Was there something before? We're getting there. So I hope you enjoyed this interview, and we'll see you next time.